Hello, my name is Joaquin Belart. I am a researcher in remote sensing with main focus in earth science, mostly in glaciers, but I've been also looking at volcanoes and landslides and so on. I would like to talk about how we have been using remote sensing to monitor the eruption of Fagradalsfjall since the spring, using a lot of optical remote sensing data, in particular stereo images. And what we did is when we knew that there was going to be an eruption, we activated a system to an emergency system of Pleiad in order to acquire over the first 10 days of the eruption images of this area. Actually, we were taking images of the whole Reykjanes area, which is quite a large area. The satellite would pass around 12:30, and it would send the data to us, and we would then process it very quickly. We would do all the stereo processing, so creating an elevation model and adjusting it also in order to be sure that there is no bias of elevation in comparison to a pre-eruption surface. After the emergency tasking of Pleiad stopped, then we continued this with airborne data. So we've been flying there regularly every 5 to 10 days on average, except when there has been a lot of bad weather, like in this past summer. And every time we were mapping the whole area, and we were creating elevation models. And so the timing was usually 5 hours since the time of acquisition until we had the volumes, especially with satellites, that's easier to process. With airplanes, it's a bit slower, but not more than 8 hours of work since the time of acquisition until we would give the latest volume, the latest ortho image, and so on. So it's been quite a broad type of techniques and mapping that we've been using here, and it has proven to be very, very useful. So we are doing digital elevation models repeated over time, and what is the most important about that is that they need to be accurate. They need to be placed correctly in the right location. That's how we can do that, for example, with ground control points, because they need to give the exact value of elevation at each cell in space over the whole eruption. And this has to be done then with photogrammetry. So with photogrammetry, you could have like a very simple way to put all the images together, and you can create a simple 3D map that you can rotate. And this has been done also through the eruption, and this is done regularly as soon as we are done with acquisition of photographs from airplanes. And this is really useful for people just to understand and just to visualize things. But this is not accurate still until we have a full reference with proper coordinates in the space, in coordinates in the Cartesian 3D system. And this can be done with ground control points, or with the satellite images, we have it with the orbits of the satellite. So we are making these 3D models accurate in the space. And that's how we can then compare them to each other and calculate a volume and an diffusion rate. And I think that is quite important, that we can do this in real time, to create these digital elevation models in real time. This has been quite unique about this eruption, and we can just provide them to different people, and this is used for many purposes. For example, also for lava flow modeling, or for us, we understand much better. We get the lava thickness by comparing them, etc.
Hi, my name is Gro Birkefeldt Møller Pedersen, and I'm a researcher at the Institute of Earth Science within the Nordic Volcanological Center at the University of Iceland. And in this video, I'm going to talk about how we have used stereo-photogrammetry for mapping and monitoring of effusive eruptions, namely the Fagradalsfjall eruption 2021. Effusive eruptions are eruptions that erupt fairly quietly, unlike explosive eruptions. And basically you have lava oozing out, producing either a big lava field or lava domes, depending on whether you have mafic or felsic eruptions. The eruptive products primarily consist of the lava flows, but you also have pyroclastic deposits around the vent, making up the ramparts of the craters, etc. What we really want to know is the size and the rate with which these eruptions are growing. So that can be the volume or the mass and the effusion rate. So that is basically a measurement of the volume flux per second. This is important because we use this estimate to evaluate the hazard connected to these eruptions. It can be the extent of the lava field, the advancement rate, and we also use these numbers for lava flow modeling. When you are measuring effusion rate, you can either measure instant effusion rate or time average discharge rate. The instant effusion rate is short-term measurements that you could, for instance, can do in the field, where you can observe an open channel, so you have the idea of the width of the channel, the depth of the channel, and you can also observe the flow within the channel, which provides you a measurement. These measurements can basically tell you something about the flow within that channel or within a lava tube, but can be prone to short-term changes and might not display the overall changes in the the effusion rate within the lava field. Multiple other methods exist in order to monitor the time average discharge rate, and here we focus on the technique stereo-photogrammetry. So what you want is that you have a plane or a satellite flying over the eruptive sites and taking pictures. These pictures have to have an overlap between 60 to 80% in order to be able to make topographic models. So in the Fagradalsfjall, we use stereo-photogrammetry, and we basically have made many different surveys. Some of them have been with a plane and others have been with satellite. And here you see an example of an orthomosaic generated after a plane flew over the eruptive sites on the 26th of April. You can see we have digitized the outline around the lava flow, so we have a very clear idea where the lava flows are. And we can see the open channels and the plume from the eruption site. From the survey, we also get a topographic model that you can see here. The lower elevations are in white and the higher elevations are in red. And from multiple surveys, we can then construct a time series of topographic models and create time differences between each survey. So from the time series of topographic models, we can make thickness change map. And here you see an example of a thickness change map from the 26th of April and the 21st of April. And you can see the areas where there have been changes between these two surveys. The blue areas is where we have had added volume, and the red areas is where there has been removed volume. So you can see the new lava flows that have been forming, either stacking up top of previous lava flows or expanding into new areas. The red areas are mainly within the craters and channels, and is where we have experienced a deflation, basically because you have fluctuating lava levels in these areas. If you subtract a pre-eruption digital elevation model, so basically a topographic model before the eruption started, with the new survey, then you get a thickness map, which basically shows you the entire thickness of the erupted products between the survey and the time before the eruption started. And here you can see the thickness map from the 26th of April. In blue, you see thicknesses up to 50 meters, and in red, you see thicknesses down to 0 and 1 meter. With repeated surveys, we can make a time average discharge rate curve, or the evolution of the time average discharge. And that gives you an insight to how the eruption is developing, and potentially also how it might project into the future. Is it declining and potentially finishing? Is it stable? Or is it in fact increasing? These different type of scenarios is giving us implication of how we have to prepare for the future, near future of the eruption. Here you see a graph showing the volume and the time average discharge rate for the Fagradalsfjall eruption until the 8th of August. You can see the volume have steadily been increasing throughout the eruption, and you can see the time average discharge rate in the beginning, the first 50 days, were around 5 to 7 cubic meters per second. After the first 50 days, we experienced an increase up to 13 cubic meters per second, and the last month we basically see that there are a bit more fluctuations that we have experienced than previously. You can also see how the area of the lava field have been developing over time, and it more or less have increased linearly until day number 100, but we see now that it's flattening out a bit. as the lava flow is thickening. One of the great advantages of stereo-photogrammetric monitoring is that we don't only get the volume and the time average discharge rate, we also get orthophotos, we get thickness maps and thickness change maps. And these products have been used in various ways in the hazard assessment and communication of hazards in the area. The ortho images have been used for making hazard maps and communicating the hazards around the eruption site to responders, the rescue teams, the police, etc. But also the tourism industry have greatly benefited from this, and they have been made maps of the suggested hiking routes you should take in the areas. So the thickness change map have provided lots of helpful information with respect to monitoring the lava emplacement. We can see the new areas where there have been new lava flows. We can see where the lava was deflating. We have seen where the vents are building up, but we can also see where the lava has been inflating. So lavas can basically be inflating slowly, and it can be difficult to see, especially if you're observing a big area. In this case, we can see concentrated inflating at the southern end in Geldingadalur, which was quite important because that was an area situated just above some hiking paths below this valley, which was basically filled to the brim and about to spill out over the hiking path. And then we have used the thickness maps for lava flow modeling. We have done two different things. We have used the thickness maps in order to evaluate how good our lava flow models are. So you have a thickness map from a survey, and then you have run a lava flow model with the same volume, and you compare how good is your model doing. Another way we also have used the thickness map is basically to make a new topographic model and run the lava flow model on top of the new topography, and thereby get information about where the lava is likely to run. And this has been really helpful in order to give information to the police and the rescue teams in order to plan for where the lava will flow next. So to summarize, in this video you have seen how we use stereo-photogrammetric monitoring to measure the time average discharge rate and the volume of the eruption at Fagradalsfjall volcano. We have also used the derived products ortho images for map making, the thickness change map for lava emplacement monitoring, and the thickness map themselves in lava flow simulation. If you want to learn more about this, you can check out this list of references.